Did AI solve one of mathematics' oldest unsolved problems? OpenAI says so, but debate is ongoing. Let's find out more in this presentation.
On July 10th, OpenAI made this massive, totally shockwave-inducing claim. They announced that their brand new AI model, GPT 5.6 Sol Ultra, actually solved one of graph theory's most famous, most stubborn open problems. We're going to break down exactly what this problem is, how the AI supposedly solved it, and why the entire academic world is absolutely buzzing right now.
To really grasp the gravity of this moment, we've got to talk about the number 50, because that is how many years this specific mathematical puzzle has sat completely unsolved. Since the 1970s, the most brilliant human minds have thrown literally everything they have at this problem. We're talking supercomputers brute-forcing millions of examples, people spending their entire careers just chipping away at the edges, and yet a universal proof has totally evaded the math community for 5 decades. It's been this colossal mystery. Well, until possibly right now.
All right, Section 1, the AI breakthrough claim. Okay, let's dive into this. On July 10th, which was literally just one day after the public launch of the GPT 5.6 model family, OpenAI published a very short, highly technical paper. And the claim was as bold as it gets. They stated their advanced reasoning model, GPT 5.6 Sol Ultra, had independently produced a proof for the Cycle-Double-Cover Conjecture. The suddenness of this announcement caught pretty much everyone off guard. I mean, this wasn't the result of some massive human-led research lab churning out papers over years. It was an AI system fresh off the launch pad dropping a potential solution to a legendary math problem. But actually, scratch that. Before we go declaring that artificial intelligence has totally conquered human mathematics, we need to make a really crucial distinction here. A proof claim is not an accepted theorem. We have to be perfectly objective. In the realm of high-level mathematics, new proofs are never just accepted because they look convincing or just because they come from a respected tech giant like OpenAI. They're only accepted after independent experts, veteran mathematicians, spend months carefully scrutinizing every single logical step. At the time of this explainer, that rigorous verification process is still actively underway, so we really don't know for sure if the AI is right yet.
Moving on to Section 2, the Cycle-Double-Cover problem.
So what exactly is this problem that stumped us for so long? The puzzle is known as the Cycle-Double-Cover Conjecture, and it was proposed independently by 2 mathematicians, George Sakaris and Paul Seymour, back in the 1970s. It's actually surprisingly easy to grasp, even if you don't have a background in advanced graph theory. Let's ground this abstract math in a real-world scenario. Just imagine a city made entirely of roads and intersections. Your goal is to ride your bicycle around the city in loops. But there are 3 strict rules for your bike ride. First, you've got to start and end your ride at the exact same intersection. Second, no teleporting allowed. You have to ride continuously along the roads. And third, you can never get stuck halfway through. You absolutely must complete the loop. In mathematics, this kind of closed, continuous ride is what we call a cycle.
Now we arrive at the core challenge of the conjecture. It asks a deceptively simple question. Can you choose a collection of these loops, these continuous bike rides, so that every single road in the entire city is ridden exactly twice? Not once, not 3 times, exactly twice. At first glance, this sounds incredibly reasonable. You'd think you could just chart out a bunch of overlapping loops until you cover everything perfectly. But trying to do this universally for every possible city map you could ever imagine is just a monumental task.
Now, what's really interesting about this is there's one major exception to the rule: bridges. Imagine a map that has an island, and there's only one single road leading to it. If you ride your bike across that road to the island, well, you're trapped. There is no alternative route back to complete your continuous loop without turning around and retracing your exact steps, which totally breaks our rules for a valid cycle. Because of this structural impossibility, the conjecture officially only applies to road networks, or graphs, that do not contain these bridges.
But even when you remove all the bridges, the math really doesn't get much easier thanks to something mathematicians playfully call snarks. These are incredibly stubborn graph examples. Think of them like malevolent little puzzle pieces that seem specifically designed to break every obvious strategy you throw at them. And here's the kicker about mathematical proofs. A proof has to explain why a rule is always true for an infinite number of possibilities. If a proposed proof works perfectly on a million normal maps but fails on one single snark, the proof is dead. It's completely invalid. Snarks are the primary reason human mathematicians have been stuck on this for 50 years.
Section 3. The AI's unique approach.
So how did GPT 5.6 Sol Ultra actually tackle this seemingly impossible puzzle? How did an AI navigate around the snarks and infinite possibilities where human intuition has historically hit a brick wall? So the crucial point is how the AI shifted the perspective of the problem entirely. Humans usually try to solve this by constructing loops one by one, manually tracing paths. But the AI took a different, incredibly elegant approach. The intuition behind the AI's proof involves placing 2 colored stickers on every single road. Instead of searching for complete loops, the AI's logic assigns colors in such a precise way that if you only look at one color at a time, the roads naturally and automatically join together into perfectly closed loops. It's a brilliant conceptual leap, right? Constructing an underlying structure that forces the loops to emerge on their own rather than hunting for them manually.
The technical achievement behind this is just staggering. OpenAI stated that GPT 5.6 Sol Ultra achieved this using a multi-agent ultra reasoning mode. Basically, this means different AI agents were debating, checking, and refining the logic together. And even more mind-blowing, the AI reportedly finished the proof in under an hour. No way, right? 50 years of human struggle, potentially resolved in less time than it takes to watch a movie. Finally, another AI model, Codex, was brought in to assist in formatting the final mathematical manuscript, perfectly preparing the complex notation for humans to read.
Which brings us to Section 4, how the internet reacted.
As you can imagine, when a claim this massive hits the public, the reaction is intense. The announcement just exploded across platforms like Reddit and Hacker News. It perfectly captured the grounded skepticism of veteran mathematicians, with one user on r/mathematics stating, "We'll wait until the broader community actually takes a look at it to evaluate if it's more than just pretty notation." And honestly, this is the healthy scientific way to react. Large language models are notorious for hallucinating or creating logical arguments that look structurally sound but contain fatal flaws the second you look closer. The professionals are absolutely demanding rigorous peer review before celebrating.
Meanwhile, others kind of used humor to process the sheer speed of the AI's accomplishment. Check out this quote. It's a joke about the hypothetical prompt the OpenAI engineers might have used. Spend at least 8 hours on this before even thinking of returning or giving up. It highlights the stark contrast between human and machine effort. A grad student might spend years agonizing over this conjecture, but the AI reportedly crushed it in under an hour. As one user joked, like Michael Jordan taking it personally.
But underneath all the skepticism and the jokes, there is a very real, very raw anxiety emerging in the academic community. Look at this reaction from r/math. Seeing news like this daily is basically a humiliation ritual. What are we even supposed to do as grad students? This really highlights a profound existential dread. I mean, if AI can solve 50-year-old open conjectures in an hour, what is the role of the early career mathematician? It's a sentiment that's echoing across university halls everywhere right now.
Section 5, why this changes everything. So, what does this all mean? Whether you're a skeptic, a joker, or an anxious grad student, we are standing at a major crossroads here. We need to zoom out from the Cycle-Double-Cover Conjecture and look at the broader implications of this event, because this shifts the entire paradigm of human knowledge generation. First, just a quick reminder of reality. History is full of convincing proofs with hidden flaws. We've got to remain completely impartial here. The AI's proof could be wrong. Subtle mistakes involving hidden assumptions or incomplete arguments can take years to uncover. As of right now, no fatal flaw has been found in GPT 5.6's work. But the absence of a known mistake is not the same thing as confirmation. It's still an open problem until the human consensus says otherwise.
And this brilliantly illustrates the massive shift we're witnessing, regardless of whether the proof ultimately holds up. For years, AI was viewed purely as a useful assistant. It checked our calculations, it generated boilerplate code, it helped us organize our thoughts. But this event signals the dawn of AI as an original contributor. We're now dealing with an intelligent system capable of producing sophisticated, highly original mathematical ideas that demand serious, professional evaluation. The AI is no longer just the calculator, it legitimately has a seat at the drafting table.
Which leaves us with a pretty profound final thought. When an AI produces an original mathematical argument, especially one it generates in less than an hour, how do we efficiently verify it? If AI can generate complex theorems infinitely faster than human peer reviewers can dissect them, we are going to hit a massive verification bottleneck. Who checks the math when the machine outpaces the mathematicians? That is the new puzzle we have to solve. Thank you so much for joining me for this explainer. Definitely keep your eyes on this developing story, and I'll see you next time.